Okay, so what I want to cover then is a sort of an overview of kinematics, getting right into accelerated motion, at least the basics of accelerated motion. Kinematics. Oop, what's going on here? Okay, so essentially just the study of motion. And we've already laid down these concepts like displacement, velocity, and so on. So I'm not going to repeat that. But we'll start first with just reminding you about what you sort of already know. So the definition of velocity is the change in displacement as time goes by. Okay, so if we have a number line, I'll just do this. If we have a number line, there, that's better. One more time. We have a number line, okay. As time goes by, if an object is changing position, in space, we can figure out its velocity as the rate of change in position, okay. And the rate of change in position is called the displacement, okay. So we get a velocity as a displacement over time. The usual units for velocity are either in meters per second or kilometers per hour. Velocities can be negative because if the object is moving in the negative direction on the number line, it's moving to the left, you'll get negative values for that. Negative values simply indicate a direction to the left or down or whatever we've defined as being the negative direction to differentiate from velocity in the opposite direction. Speed is like this, but it's a bit different. Speed does not consider direction, just considers total distance covered divided by time. So that's what we've accomplished so far. And so far we've been dealing with constant velocities. This is where, say, something has like a velocity of something like, say, 2 meters per second for some given amount of time. Well, how far do they move? They go for 2 seconds, they'll be 4 meters from where they started, and so on. And we've looked at the graphs of this type of motion as well. And we found that they create fairly simple graphs. So if on the y-axis we have position and on the x-axis we have time, we get graphs like this with our constant motion, okay? So there might be an object moving fairly slowly, and here might be something moving much faster. You can tell this because the position is changing for a small amount of time. All right, we also learned that this formula here that we have that defines velocity can be looked at in a different way when we're talking graphically, all right? So something that we know about is that if we were to find the rise and run of one of these, just fix it a little bit, okay? Or, in sort of more mathematical terms, look at the slope. Well, the slope of this graph is going to give us the velocity, okay? The slope is going to give us the velocity. The reason being is delta D is our change in position, or our rise. So our rise is the equivalent then of delta D, and our run is the equivalent of delta T. So, if we say that M slope is rise over run, here in this real world example, we say velocity is equal to delta D rise over delta T run. So change in displacement over change in time, or I should say change in position over change in time. So then we went on to just briefly examine velocity time graphs. We haven't really gotten too far into that, but let's see what would happen if we were to map out what's happening with velocity versus time for this object, or these two objects. So essentially, they're both moving in the rightward direction. We have positive velocities in both cases. We have positive slopes in both cases, right? If we were to have a negative velocity, we'd end up with a negative slope. And this is just indicating where in space this is happening. So this is all happening to the right of the 0 on the number line, okay? So we'll just kind of track this over here maybe by drawing ourselves a little number line. So there's 0. That corresponds to a position of 0 here. There's nothing happening to the left of that. Both of these objects start, the green and the orange, at 0, okay? And they move off through space. The green object is moving more slowly. So in some amount of time, it might only, in X amount of time, it might only go that far. whereas the orange object moves much farther, the same amount of time, right? It'll be like way off up here somewhere by the time their times are equal. Okay, so does that make sense so far? So now if we were to map out their velocities, we would see, well, the velocity here is much greater. We get more distance for a given amount of time. The slope is higher. If we were to transfer that onto the velocity time graph here, we would see that it's a high velocity up here somewhere. Okay, and the green guy is moving much more slowly, but in both cases, the velocity is unchanging. It's unchanging because the slope over here never changes. It's unchanging because we've defined this problem by saying these just travel at constant velocities the whole time. So what we're doing here, in essence, although it seems quite simple, is we're translating one type of graph into another type of graph. So the way to say this then is to generate a velocity time graph, we use the slope of a position time graph generates the velocity time graph. Okay? But now the question is, can we go the other way around? Can we figure out a displacement based on a velocity and a time? And the answer is absolutely we can. We take this formula and we perform some algebra on it, right? We're dividing the right side by t. So if we multiply both sides by t, this formula converts itself to say the change in displacement is equal to whatever velocity I have times whatever time interval I do that velocity for. Okay, so this is the idea of saying I'm traveling at 100 kilometers per hour for 4 hours. How far did I go? I must have gone 400 kilometers, right? We can find that from this graph, right? Have a look here. This is our velocity as defined, right, by this value over here. I don't know, say it's like 1 and say this is like 10, for instance. And this might be our time, say it's like 10 seconds total. Well, we just said displacement is equal to velocity times time. Look what we're doing. We're taking a velocity, right? That's this here, it's the height, times a time. What we're actually doing is we're finding the area of a rectangle here, aren't we? We're taking the velocity value, v, that's this green line, and we're multiplying it by a time. So the area here, the area equals a displacement change. Okay, so we can actually work backwards too. We can say, we can take this velocity graph, we can create a position graph or a change in position graph from this information. Now, we got to be careful because this is only going to tell us the displacement or the change in position. It can't tell us where we started because, for instance, if we took this line, we started it up here, right? So instead of starting there, maybe we're starting like over here somewhere. That would not change anything about this graph. This is velocity, the slope is still the same, right? So you're still going to get the same graph. So you have to be a little bit careful. This does not tell you where this is happening. You need more information to know where it's happening. But it does tell you how much the position changes, or the delta d, right? It tells you this right here, right? How much that position changes in time. All right, and you can do the same for here. So you'll see if I'm traveling at a higher velocity, okay, I'm going to have a larger displacement change, just so you can see here, in a given amount of time. So that is just simply this. Delta D equals V times T. So this is the area under the VT curve. So while we're on this topic, let's introduce the concept of acceleration. So right now, there is no acceleration. It's 0. But acceleration happens, okay, acceleration happens when velocity is changing. So you can imagine right now, in a case where an object is just traveling along at a constant velocity, there is no acceleration at all, okay? So you get a flat line on here, but if this velocity were changing, then all of a sudden you'd have sloped lines on your velocity graph, wouldn't you? If the velocity was going up, we could pull this up and have it sloped up like this. If the velocity was decreasing, we could pull it down like that. If the velocity was negative, we could have that line down here, okay, traveling in either direction. So we're going to start to examine different situations that do have accelerations, okay? If I were to make the acceleration time graph of this, it would just be a flat line of 0. It would be really boring and sort of pointless, okay? However, you will see a pattern develop. The slope of the position time graph begets the velocity time graph. The slope of the velocity time graph begets the acceleration time graph. The area under the acceleration time graph begets the change in velocity graph, and the area under the velocity time graph begets the change in position graph. Let's talk about accelerated motion now. Much more interesting, I would say. Okay, a little harder to deal with, like with your brain, but much more interesting generally. Okay, so let's think of a scenario where we're going to have like an increase in velocity. Oh, come on. It is a circle, but you can't see it. There we go. So imagine we're looking at this from the side here, and this is a ramp of some sort. And we were to release this ball and have it roll down the ramp, okay? Now, let's just imagine that we're looking at the, oh, for goodness sake. At this ramp as a number line, okay? So let's say this ramp's a number line. And let's put, just to be easy here, let's start with 0 here and have this object travel down the path here. 1, 2, 3, 4, 5, 6, 7, 8, 9, say. Okay, and we'll say the initial velocity of the ball equals 0. Actually, initial velocity is often called a u. So we say u equals 0. You might see that at some point and wonder what's going on. But we also call it vi. It doesn't really matter what you call it. It's important that you understand it. So if we were to look at the velocity, or even just say look at the position of the ball every few seconds, something we might notice is that the distances between balls at different times is going to start to increase. Okay, so let's say we have a camera with a strobe shutter and it takes a picture at even time intervals, say once every like quarter of a second or something like that. Okay, so these are representing where the ball is after each quarter of a second. Okay, say something like that. I didn't put units here, so that could be legit. So what we're seeing here is at first, in the first second, in the first second, the ball covers, a relatively small distance. Then in the second second, it covers a larger distance. In the third second, an even larger distance, and in the last second, an even larger distance. So what it's doing, or what we're saying here, is if each one of these seconds represents the average velocity for the second, right, the v_av, well, what's going on with time is as time goes by, that average velocity grows, right? It starts at 0, and somewhere over here, its final velocity is, much, much higher than 0. Some value that's way higher than 0. I shouldn't put an equal in there. That's confusing. Some value higher than 0. So now we have a much more interesting scenario, and if we start to lay down what the graphs are going to do here, okay, we'll start here. I'll try to put them all in a line. Oh, no, it's probably better to have one above the other. Whatever, doesn't matter. Okay, so we're starting at a position of 0, right? So my positions are here and my time's here. And what I'll notice is as time goes by, and time, remember, always ticks by uniformly, right? You can't accelerate time. Time always ticks along at the same rate, unless you're moving really fast, but don't worry about that for now. And we start at a point of 0, a position of 0, and we cover a little bit in the first, in the first second, and we cover a little bit more in the second, and a little bit more in the third, and a little bit more in the fourth, and so on, right? So we get to here, maybe to here, and way up to here, and what you've created is a curved line from this information, right? Moving towards the positive, its velocity speeding up and getting higher. It's covering a larger amount of distance in equal amounts of time. So you get a parabolic relationship here. Okay, and before we said that velocity is equal to delta d over delta t. Well, if we just did that for this motion, okay, we might be a little bit, we might be fooling ourselves a little bit here. I'm just gonna exaggerate this a little bit to help us see what we need to see here. There, we'll do it more like that. Because if I just go, total distance covered divided by total time, I'm just going to get a single number, right? So to illustrate what I mean by that is if I were to just look at this, as a whole motion and go my final position, subtract my initial position, divided by the time interval, that would imply that I only had one velocity for the whole time, right? In a sense, that's not wrong, but we have to name what that is. What that would find me is what's called the average velocity for the trip, which is going to ignore, in a sense, what's really going on, okay? So if I just go delta D, the final, right, minus the initial, and the final minus the initial for time, I'm going to get this value. What this is really saying, though, is it's saying that at some point in time I was traveling fast, in fact, right in the middle of my motion, all right? Or another way to look at it is saying it's as if I traveled this constant speed the whole time, but it's ignoring the fact that there's nuance to how I moved here, okay? So what we really want to know, if we're going to talk about how velocity is changing, what we really want to know is, well, what were my velocities at all these different points in time? And in order to do that, you need to create tangents for every point in time. I mean, that's unrealistic, but that's essentially what you're thinking you're going to have to do, right? So we call this line here a tangent line. Tangent to the curve. Okay, so this tangent to the curve gives us instantaneous velocity at any given point where we put this tangent. So this is the instantaneous velocity, okay, at this point in time. And we draw a new one for later on in time, and we'll find that it's, more vertical than it was because my velocity is higher. And before this point in time, it was lower, okay? So drawing tangents and finding the slopes of tangents at instants in time will show a gradual change in velocity. Another way of looking at it is dividing the distance covered in equal time intervals and seeing that those grow, but realizing exactly what that's showing us, right? That's showing us the average velocity for the 1 second interval. To truly do this properly, you need to have an infinite number, essentially, of tangents, right? Because my speed is constantly increasing all the time. And really, we're bumping up against some concepts that you'll learn about a little bit more in calculus, okay? There are ways to find lines tangent to a curve at any given moment in time, or to generate, if you want, the equation for the velocity time graph from this. That's more advanced than what we're dealing with. We're going to look at it as simply as possible. And we're going to think about what kind of velocity time graph this is going to generate, okay? So what will happen here is there will be a smooth increase in velocity. The reason being is because the slope dictating the change in velocity, right? The slope is causing the change in velocity. It is not changing. So we have a consistent velocity change all the time. And it happens to be, the way we've set it up, a positive velocity change. So what we get from here, if we looked at each individual velocity all through time, we'd see that the velocity is essentially 0 to begin with, right? Starts with no velocity. A little while later, and this is in meters per second, a little while later it's higher and then higher, then higher, then higher, then higher, right? That's probably sensible. Time moves on regularly like this, okay? This is the same motion, but we're looking at two different aspects of the same motion, okay? This begets this via the instantaneous now of the slope of the tangent at all the different points in time, okay? So whatever I found for the tangent at like 1 second, I map over to here. Whatever I found for the tangent at 2 seconds, I map to here. 3 seconds and so on, all the way up till the end of my travel when it was much higher. And I will find that I get a linear relationship, okay? If I have a consistent straight curve like this, then I get a consistent change in my velocity, okay? Now what I can do is I can talk about this. This is accelerated motion. The velocity is always changing. And now I'm going to do something new with this. I'm going to create an acceleration time graph from this, but first I'm going to make a definition. Acceleration is found as the change in velocity over the change in time. Or if you want, another way to think about it is the slope. The slope of this graph, right? The slope of this graph is my velocity. The slope of this graph is my acceleration, okay? And now I have something to put on my acceleration time graph. Oops, like that, straight line. So my acceleration time graph now has a positive constant line on it, right? If I look, the slope here never changes. So that means on my acceleration graph, I'm just going to have a constant line that looks just like this, okay? This slope gets mapped to here and it never changes. All right, so this is the slope of a VT graph, okay? It's the rate of change in velocity. Let's just look at the units here, right? So if we were doing this, we know that the units on top are found in meters and the units on the bottom are in seconds. Therefore, velocity's units are meters per second. Now we're taking these values and we're putting them into here, right? It's like Inception, we're going like one level deeper. So now we've got a change in velocity. So we've got a delta meters per second. And we're now saying, well, what's happening there in terms of seconds? So we get the unit meters per second, which we rewrite as meters per second squared. The way I like to think about this is I am changing 1 meter per second every second, right? For instance, so after 1 second, I'm going 1 meter per second. After 2 seconds, I'm going 2 meters per second. After 3, I'm going 3. But each individual jump is 1 meter per second. I'm going up 1 meter per second, or 1 meter per second squared. So just make sure you understand, right, that since this slope never changes, when we beget our acceleration time graph, which is here, acceleration and time, that acceleration never changes because the slope of this graph does not change. All right, now we're going to look at this formula and we're going to rearrange it here, okay? So we're going to do this. We're going to say that delta V should then be equal to whatever my acceleration value is times the time that I accelerate over. See if I can make sense of this. So let's say I start at 0 meters per second, for instance, and I accelerate at 2 meters per second squared, or 2 meters per second for 5 seconds, okay? Well, after that, I should have, or what I should have is a change in my velocity equal to 10 meters per second. You can see per seconds to the -2 times seconds, one of those pops off, drops it to a -1, and there, my units agree. I have changed my velocity by 10 meters per second. Since I started at 0, by the end of this, I'll be going 10 meters per second. So what I'm really doing here is I'm taking my acceleration from my acceleration time graph, and I'm multiplying it by time. So again, I am finding the area right in here, saying the change in velocity is equal to whatever my acceleration is. Why am I putting a C there? Don't put that C. That should not be there. Whatever my acceleration is, I know, I shouldn't have done that. Times T. Don't worry about it. You'll be fine. It just should be an A. Okay? So there we go. So what we're saying then, moving back up, just like we did before, that the area under here tells us our change in velocity. If we know it started at 0 and it changed by 10, as we predicted, then the area here would be 10, right? 2 meters per second squared times 5 seconds causes a change of 10. Happens, you know, in a consistent way. And so the area here, which is delta V equals A times T. Okay, we get an area under the acceleration time graph predicting or creating the velocity time graph, and the same thing going on up this way, although it's much more complicated because now we've got to find the area of a triangle under here instead of just a flat line, but it still holds true. Area underneath a velocity time graph gives us our position change. When we have accelerated motion, however, it's not as simple as it is when we have a consistent velocity like we had in our equation above. In fact, we're not even going to worry about going this way. We're just going to accept that it's true. We sort of proved it. This is a little bit beyond this course, generating a nice curved slope from a graph like this, but it can be done, okay? So we'll just leave it at that for now. Okay, there are essentially only 4 possibilities for accelerated motion, at least from the perspective of basic kinematics, okay? Here they are. And I'm going to demonstrate this on basically on 2 ramps. I'm going to have one ramp that goes like this. I'm going to have one ramp that goes like that. So my first question to you is, which way do these ramps cause acceleration to happen? which way would acceleration happen on the left-hand ramp? Which way would the acceleration be? If I put a ball on here, which way would it go? Yeah, it's going to go to the right. And which way does this ramp cause accelerations to happen? Good, to the left. Okay, so we're going to kind of think of accelerations as a ball on a ramp, or if you want, as a push on the ball. This ramp pushes right. This ramp pushes left. Okay, so we can only have, if you want, an acceleration that is positive. We'll draw that with a little arrow, positive being right, or an acceleration that is negative. That's the only two kinds of acceleration we could ever have. That's it. There's no other kinds, right? All we have to work with is a number line, right? Here's a number. Oh, that's not a number line. It's a black line on a black paper, which does nothing. Okay. We can only be moving right or left, right? That's it. That's our only options. So let's start with a really common type of one, and that's one we've already seen. That is, let's place a ball on here and let it roll down. Okay, well, we've already seen what this generates. This will generate these graphs, okay? Acceleration and velocity are both in the same direction, right? If I let this ball go, it speeds up to the right. Acceleration and velocity are in the same direction. We speed up to the right. That will generate the following. So we'll just write it down. We've got a positive acceleration and a positive velocity. We get this. We get positive increasing slope on our position time graph. We get a velocity time graph that looks like this. And we get an acceleration time graph that is just straight up positive, right? Now let's look at a slightly different case. Let's say that instead of taking a ball and releasing it here, I do something different. I take a ball and I put it down here, but now I roll it up the ramp. Now I give it a velocity that's in this direction. Here, let's do this. I give it a velocity that's in this direction, okay? This ball will roll up the hill, but the acceleration's to the right. So what's going to happen to its velocity as it rolls up the hill? Well, it's going to decrease, right? It's going to slow down as it rolls up the hill, okay? So let's draw ourselves this scenario. So now our starting conditions are this. We have acceleration still to the right. That's set by the ramp. However, our velocity is actually in the opposite direction. So, well, seeing as how the ramp is the way it is, we should probably be careful how we draw it. Now it starts to, we said this was a 0. Well, basically we get this shape, right? No, we don't. What am I doing? Sorry. It travels towards the origin, but it slows down, okay? So this is an object traveling to the left, traveling back towards the origin, with an acceleration to the right, causing it to slow down as it goes, okay? So it starts off here, it's rolling back this way, and I'm just basing that on what I did with this one, just to kind of be consistent. Okay, so it's rolling to the left, but against the direction of acceleration. So what's happening to this now we have to be a bit careful, right? Because now we have a negative velocity, right? So our velocity is negative and it's decreasing. So we start with the high leftward velocity, right? But that decreases and approaches 0 as we roll up the hill. Our velocity gets smaller. So remember, this is the negative part of the velocity graph. There's a velocity of 0. We start traveling at a high negative velocity and we slow down, okay? And we still have the exact same acceleration, and you should be able to see that. If I were to take the slope of this graph, I'd see that it's positive and my acceleration is positive, okay? Okay, let's continue. Now let's take this ball and let's put it up here on this ramp, okay? On this side of the ramp. Let's get rid of this stuff. So we're just kind of dealing conceptually now. I mean, there's a bit more to this, but now we have a leftward acceleration, and we're going to find that as we let this go, our ball is going to be traveling leftward as well. So we have now this going on. Oops, we have this going on. We have a leftward acceleration and we have a leftward velocity. So this object will like speed up, but it'll speed up in the leftward direction. Okay. So if we want to put our position time graph, we said it's going to speed up in the leftward direction. Okay. It doesn't really matter where we start. What we really want to illustrate though is that it's speeding up as it moves to the left. So we're going to get this kind of a curve shape. It's not a very good drawing. Maybe you can do better. Okay. So look, it's got a low velocity at the beginning because it's got a low slope, but it's speeding up as it moves left. So when acceleration and velocity, when push and velocity are in the same direction, you get a thing speeding up. When push and velocity are in the opposite direction, you get something that's slowing down. Okay, so this object is getting faster and faster in the leftward direction. So on a velocity time graph, we start at a low velocity of 0, and then we increase it, but we increase it in a leftward direction. So sometime later, we have a high value for our negative velocity. Okay, and then we can take the slope of this, and we know already it's going to be a negative value. Right, the slope of this is negative, so we get a negative acceleration graph on here that's constant, right? Because remember, slope to slope, slope to slope, slope to slope, area to area, area to area, area to area. Okay, and there's only one more possibility that we can have, right? There's only one last thing we could possibly do here, and that is to roll this up the hill in a rightward direction. Okay, so we roll it up the hill with an initial rightward velocity. Stop doing that. Like this. Okay, it's going to roll up, but it's going to slow down because the acceleration on it is to the left. The push is to the left. So we still have this. Let's find another color. How about purple? So we have acceleration to the left, but we have an initial velocity to the right. This is going to cause the object to slow down as it travels to the right. So there's my position, there's my time. I'm traveling to the right, but I'm slowing down. My slope is decreasing as time goes by. My velocity is decreasing as time goes by. All right? So we start with a high positive velocity that then approaches 0 as it rolls up the ramp. It's going to slow down until it gets to a velocity of 0. And we still have that same negative acceleration that we had before. So look at my acceleration graphs. It's one of two things. It's either positive or negative. Okay, my velocity graphs are either speeding up to the right, slowing down to the left, speeding up to the left, or slowing down to the right. And I have 4 possible curves on my position time graph. So really, there's only 4 things that could be ever going on with acceleration and velocity. If you can wrap your head around this and how these generate these graphs, you're sitting pretty. Okay, I think we'll leave it there. You guys.